Right now, at this very moment, there is a school bus-sized 4,000-kilogram piece of SpaceX hardware hurtling toward the moon at 5,400 miles per hour. That's 2.43 kilometers per second. That's about 7 times the speed of sound. Impact is expected around 2:35 a.m. Eastern Time, 06:35 UTC on Wednesday, the 5th of August, 2026. The target? Somewhere near the Einstein crater. This is not science fiction. This is not the plot of a bad movie. This is real. This is happening. What you're about to witness is the spent Falcon 9 upper stage from a mission that launched over a year and a half ago. We're talking about the January 15th, 2025 launch that sent Firefly Aerospace's Blue Ghost and iSpace's Resilience. That's the Hakuto R mission 2 toward the moon. And now, after all this time, that upper stage is coming back. Not to Earth, to the moon. And here's the thing. This accidental crash. It's actually a free science experiment. It's a warning about space junk. And it is a masterclass in orbital mechanics that most people never hear about. So, let's dive in. Let's talk about what this thing actually is. It's the upper stage of a Falcon 9 rocket. Now, the Falcon 9 is a 2-stage launch vehicle. The first stage is the big one. The one with the 9 Merlin engines that you see land back on the drone ships. That returns to Earth, gets reused, and lives to fly another day. But the second stage, that's the one that keeps going. That's the one that does the heavy lifting to get payloads into their final orbits. This specific upper stage is about 45 feet long, or 13.8 meters. It's about 12 feet in diameter, or 3.7 meters. It's essentially a hollow aluminum alloy tank with a single, very dense, very powerful Merlin vacuum engine at one end. Once all the propellant is gone, it's basically an empty eggshell, a big empty eggshell with a heavy engine bolted to the bottom. In terms of mass, we're looking at around 4,000 kilograms. That's about 8,800 pounds. Some estimates put it closer to 3,900 kilograms, others closer to 4,900, depending on how much residual propellant was left in the tanks. But the point is, it's not a solid chunk of metal. It's a thin-skinned, mostly empty can, and that matters. That matters a lot for what happens when it hits. It's cataloged as 2025-010D. That's its official designation in the books. But to us, it's just that piece of SpaceX hardware that's about to become a crater. Now, this is the part that most coverage skips. This is the juicy orbital mechanics stuff that I absolutely love. Normally, when you have an upper stage for a deep space mission, you have a few options for disposal. The standard clean way to get rid of an upper stage is to either deorbit it, send it back into Earth's atmosphere to burn up, or put it into a graveyard orbit, a safe, out-of-the-way orbit where it won't bother anyone. For a mission that goes to the moon, you're on a trans-lunar injection, or TLI, trajectory. The typical options there are to boost the stage to escape velocity, which sends it into a heliocentric orbit around the sun, or to do a controlled crash of the upper stage onto the lunar surface. But that's not what happened here. After boosting the 2 commercial lunar landers, the stage performed a disposal burn, but it simply lacked enough residual propellant for a controlled deorbit into Earth's atmosphere. So it ended up in a high moon-crossing, elliptical orbit around Earth. It was basically just out there, adrift. And then, over the course of about 19 months, something beautiful and chaotic happened. Orbital evolution, solar radiation pressure from the sun, gravitational perturbations from both the sun and the moon, even residual outgassing from the stage itself, tiny little puffs of escaping gas, slowly, gently nudged its orbit over time. These are tiny forces, but they accumulate. And over months and months, they can completely change a trajectory. It's a real-world demonstration of chaotic orbital dynamics in the Earth-Moon system. Small forces, big consequences. Independent tracking by astronomers, led by Bill Gray from Project Pluto, picked this up. Using a network of amateur and professional observers, they collected over 1,000 observations, refined the orbit, and predicted the lunar impact months in advance. NASA's Center for Near-Earth Object Studies, or CNEOS, later confirmed it. They gave it a 100% probability of lunar impact. 100%. This is not a maybe. This is a definite. And what did SpaceX say? They followed the rules and regulations that were in place at the time. The stage was passivated, venting any remaining propellant to reduce the risk of an explosion. But they didn't have the fuel to bring it home. And then nature took over. Solar activity and gravity put it on this final path. All right, let's get into the numbers. This is where it gets really interesting. Time and location. Around 2:35 a.m. Eastern Time, 06:35 UTC, on August 5th, 2026. The impact site is near the Einstein crater on the western limb of the Moon's near side. It's on the sunlit side at the time of impact, which is crucial for visibility. The coordinates are roughly 19.5 degrees north, 93 to 94 degrees west. Speed, 5,400 miles per hour, 8,700 kilometers per hour, 2.43 kilometers per second. That's fast. That's roughly 7 times the speed of sound here on Earth. But here's a fun fact. On the Moon, that's actually considered a relatively slow impact. Natural meteoroids hit the Moon at an average speed of about 15.9 kilometers per second. So this is a much gentler impact than what the Moon is used to. But still, 2.43 kilometers per second is nothing to sneeze at. Angle of impact, about 34 degrees from vertical, so it's coming in at a pretty steep angle. Kinetic energy. This is the big one. The energy released on impact is roughly equivalent to 2.8 to 3 tons of TNT. That's about 14.5 billion joules of energy. To put that in perspective, that's like setting off 3 tons of dynamite. Expected crater. Now, this is where things get a little counterintuitive, because this isn't a solid meteoroid. It's a hollow, thin-walled object, so it doesn't bury itself like a cannonball. Instead, it collapses. The engine hits first, punching an initial crater, and then the rest of the stage crumples and transfers its energy into the lunar soil. The result is a crater that's estimated to be about 20 to 30 meters in diameter, that's 65 to 100 feet, and about 5 meters deep, or 16 feet. So, roughly the size of a tennis court. A shallow, wide, fresh crater on the Moon. Ejecta. This is where the real show is. The impact is going to throw up a massive amount of lunar regolith. Simulations from the University of Texas at Austin predict a broad, low curtain of ejecta that will rise 15 to 20 kilometers high and spread out over a radius of up to 183 kilometers. But that's not all. There's also a narrow, vertical spike of material that could shoot up to a height of 50 to 100 kilometers. That's 50 to 100 kilometers high. On the Moon, the total displaced mass is estimated to be on the order of 12,700 kilograms or more. The plume could be visible against the dark lunar sky for minutes. Visibility from Earth. Here's the thing. The impact flash itself, probably not visible. The crash is on the sunlit side of the Moon, and no artificial or natural impact flash has ever been confirmed on the sunlit side. So don't expect to see a bright flash with the naked eye. However, the ejecta plume has a much better chance of being spotted. The dust and debris will reflect sunlight, and with a decent telescope from the Americas, you might just be able to see it. And we've got orbiters watching too. NASA's Lunar Reconnaissance Orbiter, or LRO, and South Korea's Danuri orbiter will be imaging the site before and after the impact. Danuri might even pass within a few kilometers just minutes before impact, potentially capturing the event in real time. We'll have to wait a few days for the images to come down, but the science is going to be incredible. Okay, so a rocket is crashing into the Moon. Why should we care? What's the point? First, the scientific opportunity. This is a rare, controlled experiment. We know the mass, the approximate shape, the velocity, and the impact angle almost exactly. That is almost never the case with natural meteoroids. We have no idea what those things are made of, how fast they're going, or what angle they're coming in at. But this, we know all of that. So we get to test impact physics models for hollow versus solid objects. We get to see how a thin-skinned, lightweight projectile interacts with the lunar surface. We get a fresh crater for LRO and future orbiters to study. We get to practice tracking objects in cislunar space. That's the space between the Earth and the Moon, which is incredibly important for future Artemis missions, commercial lunar bases, and everything else we're planning up there. Unfortunately, there are no seismometers currently operating on the Moon. The Apollo network shut down in 1977. So we won't get any moonquake data from this impact, but it's a dry run for future networks. When we do have seismometers up there again, we'll know how to use them to study impacts like this. Second, the space debris and danger context. Let's be very clear. There is no threat to Earth. There is no threat to current lunar assets. This is not a disaster, but it is a warning. This highlights the growing problem of uncontrolled hardware in cislunar space. We've had accidental rocket body lunar impacts before. The most famous recent one was the Chinese Long March stage in 2022, and during the Apollo era, we intentionally crashed rocket stages into the Moon for seismology. But those were planned. This one was not. And here's the key insight. There is a regulatory gap. Current rules for space debris are much weaker for high-energy, moon-crossing orbits than they are for low Earth orbit. The FCC is starting to develop cislunar licensing, but disposal mandates are still limited. As traffic increases, with NASA, commercial companies, and international partners all heading to the moon, this becomes a real planning issue. We need to think about how we dispose of our hardware responsibly. We can't just leave it up there to wander around and eventually hit something. The broader takeaway is this: the moon is already an active impact laboratory. It gets hit by meteoroids constantly. A meteoroid with the same energy as this Falcon 9 stage hits the moon about every 6 days. So this is not a big deal for the moon. But human hardware is now adding to the natural cratering rate in measurable ways. We are leaving our mark, sometimes by accident. Let's do a quick technical deep dive because I know some of you nerds out there are dying for this. The Falcon 9's upper stage is powered by a single Merlin vacuum engine. This is a restartable engine, which means it can fire, shut down, and fire again. That's crucial for complex missions that need to put payloads into different orbits. It's optimized for vacuum operation with a high specific impulse, or ISP, which is a measure of fuel efficiency. Normally, after delivering its payload, the upper stage has a few options. It can perform a deorbit burn, which slows it down enough to re-enter Earth's atmosphere and burn up. That's the most common approach. Or, for missions going to the moon or beyond, it can perform a burn to send itself into a heliocentric orbit, effectively leaving the Earth-Moon system forever. But the fuel margins on these high-energy lunar transfer missions are tight. You have to use almost every last drop of propellant to get your payload where it needs to go. And in this case, after deploying Blue Ghost and Resilience, there just wasn't enough left for a proper disposal burn. So the stage was passivated. All remaining propellant was vented to prevent an explosion, and it was left in that high moon-crossing orbit. And then, as we discussed, the perturbations took over.